Differentiation rules addendum. In this section for chain rule, what we're going to do is we're just going to go through the proof for it, because in SL that's not part of the book, and in HL it is. Okay. Now I want you to go look through each step of the proof of the chain rule so that you can see all the mathematically rigorous steps. But I'm just going to explain the philosophy of it here. Basically, you have two functions nested within each other when you do the chain rule, right? You have like a composite function, and the outside function is the g function, and the inside function is the f function. And when you take the derivative of this function, what you end up doing is you take the derivative of g with respect to f, and then you take the derivative of f with respect to x, and you multiply them together. And that's how you get the derivative of the g function with respect to x. Okay. Now, how does that work? So, in this case, you have the g function. In this case, you have the f function. Okay. And what we're going to do is we are going to make an expression for the slope in each one, because remember, the slope of the function, as long as you make the width of the triangle approach 0, is the derivative. Okay. So you can see that for the first function, we have x as the independent variable, and we have u as the dependent variable. And so we make a slope that is delta u. This is the lowercase Greek letter delta. You know the uppercase one. It's a triangle, but this is the lowercase. So we have a little slope here that we calculate to be delta u divided by delta x, right? Makes sense, right? The change in the x variable causes a change in the u variable, and both of those are called delta something, okay? And you can see that this expression delta x is similar to when we do differentiation using first principles, the h variable, right? But when you have two functions nested within each other, you have a lot of x's, you have a lot of y's, so we start naming them with these expressions like delta x and delta u, okay? Now, we have the other function, which is the outside function g. The outside function g has as its independent variable u, and then as its dependent variable has y. Okay, so that's pretty weird, right? So the output of f is u, and the input of the g function is also u. Okay, so let's look at the paragraph next to it, which wants us to note some things about how we understood these diagrams. For every small change in x, called delta x, there is a small change in u, called delta u. For every delta u, there is a small change in y, called delta y. Okay? So, basically, for each change in x, there is a change in u. For every change in u, there is a change in y. So we can express that with a multiplication, which is basically change in y for every change in u, and then change in u with every change in, oops, I'm sorry, I started writing d's instead of deltas. Delta u, and every change in x causes a small change in u. And if I multiply those two together, then basically it's like, okay, every time I have a change in u, it causes a change in u here, and then that causes a change in y. So you see how like one kind of multiplies the other one, right? And you can like look at this as a fraction, and then you can see that, hey, they kind of cancel each other out, okay? So as a result, we can see that it's equivalent to delta y divided by delta x, right? And so basically what happens is you're gonna do a limit as the delta x's and the delta u's approach 0, and as a result, these finite triangle sides, delta x, delta u, etc., become infinitely small triangle sides, and then you end up with dy du and du dx, which are 0 length but have a finite value. Okay? All right. Now for product rule, we're going to look at the same thing. We're going to look a little bit at the proof, because in the SL book they don't talk about the proof. And we're just going to talk about the strategy of the proof, not about the rigor of the proof. But basically when you do product rule, you have a function y which is equal to two functions multiplied times each other, u and v, right? Let's say that this red line here is mapping out the path of the combined function u times v. The height at this point is uv. Now delta x later, sorry, this is delta x, not delta v. Delta x later, the height of the function is now u plus delta u times v plus delta v. Okay, so if we wanted to figure out like the difference in this height from this height, we're starting to look kind of like at the derivative of uv, right? So how do we do that? We're going to take this expression and we're going to FOIL it. Okay, if we FOIL it, then we can kind of see how much bigger it is than uv. Okay, so let's do that. So we're going to FOIL this, and we're going to end up with uv plus v delta u plus u delta v, and last of all we have delta u delta v, right? Now what happens is if you compare this new expression with the original expression here, you can see that the first term is the same as this term, okay? So that's the part that you can see is like the same, all right? Now what is the change? The change is these three terms here. Now what happens to these three terms? Well, the two of these terms are kind of bigger than the other term. Remember that delta something is a length which is going to be shrunk down until it's infinitesimally small, right? But this term here, delta u times delta v, is like even smaller, because it's like an almost zero thing times an almost zero thing, which is like a doubly zero thing. If you look at the other two, you got a v, which is a significant length that is not anywhere near zero, times delta u, which is close to zero. And here you have u, which is significant length not close to zero, times delta v, which is close to zero. So if you have like a thing that is not zero times something that is close to zero, it's not going to be as small as delta u delta v, right? Which is two things that are like really small, okay? Delta u delta v is going to be disregarded when you take the limit, because it's like so much smaller than the rest, and it kind of goes to zero, okay? The other ones become part of the product rule, right? So like for example, delta u times v is the part that eventually becomes du dx times v. And u times delta v is the part that becomes u dv dx, okay? And those are the two main parts of the power rule, right? Now delta u delta v, it goes to zero, is assumed to be zero because it is, much smaller than other terms. Okay, now we're in the implicit differentiation section on page 542. And here we are going to do our first ever implicit differentiation. And I'm going to show you how to do it. It's easier to see it done than it is to explain how to do it. So I'm just going to show you. But basically, you do implicit differentiation whenever you get a situation kind of like this one, where it's very difficult to express the function as y equals blah, blah, blah. Up until now, all of our different derivatives were done on expressions that had equations with y on the left and all the x's and other things on the right. And sometimes you get something like, a circle equation, which is difficult to separate in that manner. So the thing is, you can take a derivative anyway, okay? The only thing you have to be careful of is when you do take the derivative of y in this case, you do need to do the chain rule on it, okay? Because we're taking the derivative with respect to x, and we can't just say, oh yeah, y dash, or, whenever or like 2y or whatever, because if you take the derivative and you say that the derivative is 2y, you still haven't taken it with respect to x, you've taken it with respect to y. Okay, so you need to do the chain rule of y whenever you do that. And let me show you how it's done. Okay, so if you want to take the derivative of x squared with respect to x, we know how that's done. The derivative of x squared is 2x. If you want to take the derivative of y squared, you would say, oh, I'm going to take the derivative of y squared. That would be 2y. Okay, but then you've just taken the derivative with respect to y. Now you need to multiply it times the derivative of y, like as in the chain rule. And the derivative of y, we just write dy dx. The derivative of y with respect to x. Okay? And then on the right side, we have 4. It's just a number, a constant. When we take the derivative of that, we get 0. Okay? So now we have another equation in which we took the derivative of the left side and the right side implicitly. Why do they call it implicitly? Because explicitly would be we have y on the left by itself, we have everything else on the right, and we take the derivative of the left and we get dy dx, and we take the derivative of the right side and we get, an expression with a bunch of x's in it. Now that we have everything implicitly differentiated, let's make an expression with dy dx on the left side and everything else with x's and y's on the right side. Okay? So how we're going to do that is, first we're going to subtract 2x from both sides. So we'll get 2y, and I'll use the y dash notation here just to make it quicker. Negative 2x. Okay? And then I am going to divide both sides by 2y to get y dash by itself. So I'll have y dash equals negative 2x divided by 2y. Now I'm going to simplify that by crossing out the 2's, and I get negative x divided by y. So my derivative of y dash I discovered to be negative x over y, which kind of looks weird probably to you because every single derivative we've had up until now didn't have y as part of the derivative. And we're going to see later how you can get rid of that if you want to. But basically, that's what we wanted to do for now. Okay? Now let's do a few easy problems here. Just remember that whenever you take the derivative with respect to x of y, you need to do the chain rule and write down dy dx afterwards. Otherwise, it's pretty much the same as taking the derivative of x with respect to x. Okay, so when you take the derivative of 2x, pretend you're taking the derivative when you're taking the derivative of 2y, pretend you're taking the derivative of 2x. If you take the derivative of 2x, your result will be 2, right? Now, in this case, you just need to be careful because when you do take the derivative of 2y, you do need to do the chain rule for y. So instead of getting 2 with nothing after it, you get 2 dy dx. That makes sense, right? The derivative of 2 times y would be the derivative would be 2 times the derivative of y with respect to x, right? Okay. I made a mistake on this one before, so just ignore what's written after this segment stops. And remember that the answer to 1a is 2 times dy dx, right? So the derivative of 2y would be 2 of y cubed. We would write 3y squared, and then we would multiply that times the inside of the squared, which is dy dx also. And derivative of y to the 4th would be 4y cubed times the inside of the power there, which would be dy dx. And the derivative of y to the negative 2 would be negative 2y to the negative 3 times the inside of the exponent, which would be dy dx. And finally, x squared y. This is a little bit more difficult, right? X squared y, that's a product. So we need to use the product rule. So we're going to do x squared times the derivative of y plus 2x times y. Okay, so we did the product rule on that. All right, now let's move down to the last problem here. Find dy dx if y squared minus x squared equals 8. Okay, so let's take the derivative implicitly of both sides. So we will have 2y dy dx minus 2x equals 0 because the derivative of 8 is 0. And then we're just going to solve for dy dx like we did with the circle last time. So we add 2x to both sides, and we'll get 2y equals positive 2x, or 2x, sorry. Yeah. And then I'm going to divide both sides by 2y, and I'll get y derivative equals 2x divided by 2y. And then I'll have, simplifying, crossing out the 2's, I'll have the derivative is equal to x divided by y. You can see that this is a little bit different than before. We had negative x divided by y in the case of a circle. In this case, which I believe is like a hyperbola with diagonal asymptotes or oblique asymptotes, we end up with the derivative of y being x divided by y. Okay? Last one here. I have no idea what kind of function this is, but it doesn't matter. We can still take the derivative of it, right? 2x plus, now we got a product here, so we do x times the derivative of y plus derivative of x, which is 1, times y equals 0, because the derivative of 4 is 0. Now we're going to subtract 2x and y from the left side and the right side, and we'll end up with x y dash equals negative 2x minus y. Then we're going to divide both sides by x, and we get y by itself, y dash by itself on the left, and we'll have negative 2 divided by x is negative 2, negative y divided by x is negative y divided by x. So that is our derivative for this function. Okay, and that is the end of page 1 of the addendum.